about gravity for a second. We all know it as the force that glues us to the Earth, right? Apples fall down, not up.
Pretty intuitive stuff.
Exactly. But what if I told you that gravity's reach is so immense, so fundamental that it can even bend light? Yes, light itself.
Hmm.
And it's not just, super dense things like black holes or whole galaxies doing the bending. Even a planet in our own solar system, like Jupiter, causes a measurable curve in the path of starlight passing by.
It really does.
Did you know that? That a planet, even one as familiar as Jupiter, has this kind of influence on something as seemingly, well, weightless as light. That's what we're diving into today.
Exactly. This deep dive is all about this fascinating idea, gravitational light deflection. And yeah, we're going to focus on Jupiter as a case study. We're drawing from some really compelling recent scientific observations that let us actually see this effect in action around the giant planet.
Yeah, we've got some fascinating scientific papers here detailing these observations, the really precise measurements of how Jupiter bends starlight. It's kind of like getting a behind-the-scenes look at how scientists test the very foundations of our understanding of gravity.
It really is putting theory to the test.
So our mission today really is to understand how this bending of light around celestial bodies confirms and maybe even refines our theories of gravity. And we'll be shining a special spotlight on these latest findings involving Jupiter.
Sounds good.
Okay, let's unpack this. How does something without mass, like light, actually get bent by gravity? What's the mechanism?
Well, at its heart, it comes down to Einstein's theory of general relativity. The really revolutionary idea here is that matter and energy don't just exert a force across empty space.
Right.
Instead, they actually warp or curve the fabric of space-time itself. Now, light, even though it's massless, still has to travel through this warped space-time. So its path ends up being curved by these distortions. Think of it like this. Gravity doesn't just pull, it actually warps the very stage upon which everything, including light, has to move.
That classic rubber sheet analogy comes to mind again, doesn't it? You roll a marble across a flat sheet, it goes straight.
Yeah.
But if you put a heavy bowling ball in the middle, it creates this dip, and now your marble's path curves as it rolls past.
Exactly.
So instead of marbles and rubber sheets, we're talking about massive planets and the actual structure of the universe being warped.
Precisely. And while the full mathematical picture involves some pretty complex equations, for situations like light bending in our solar system, scientists often use a more simplified approach. It's called geometrical optics, and it helps predict the amount of deflection.
Okay.
There's a key formula that helps us calculate this angle of bending. It looks a bit intimidating at first glance, maybe, but it really boils down to a few key factors.
Okay, let's not scare everyone off with equations just yet, but what are the main ingredients? What determines how much the light bends?
Well, essentially, it depends on how massive the object doing the bending is. So in our case, Jupiter, and crucially, how close the light passes to it. That's the impact parameter.
Okay, mass and proximity. Makes sense.
Right. And there's also a fundamental constant involved, the speed of light. But what's really interesting, I think, is that even before Einstein, there was this idea that gravity might bend light based on Newtonian physics.
Oh, really? I didn't know that.
Yeah, but that prediction was different from what Einstein's theory came up with. Einstein actually predicted twice the amount of bending.
Wow, double.
Yeah, double the effect. That was a huge difference, a really major point that scientists were incredibly eager to test observationally.
Double the bending. That's not a small tweak at all.
Mm-hmm.
So how do scientists sort of standardize this? How do they express these predictions in a way that lets them compare different ideas about gravity?
They use something called the parameterized post-Newtonian approximation, or PPN for short.
PPN.
Think of the PPN framework as a kind of standard toolkit, or maybe a ruler, that scientists use to measure how well different gravity theories stack up against actual real-world observations.
Got it.
And within this PPN framework, there's a parameter, often called gamma, the Greek letter gamma, that's particularly important for light bending.
Gamma.
Now, in Einstein's general relativity, the value of this gamma parameter is exactly 1. Nice and simple.
Okay.
And the results from experiments, like measuring light bending, are often expressed in terms of a slightly different combination. It's 1/2 times 1 plus gamma. So if GR is right and gamma is 1, that factor becomes just 1.
I see. So if they measure that factor and it comes out as 1, it supports general relativity.
Precisely. And for light that just grazes the edge of the sun, general relativity predicts a bending of about 1.75 arc seconds when you plug in gamma equals 1.
1.75 arc seconds. That sounds incredibly tiny.
It is. An arc second is 3600th of a degree. So, Yeah, it's a very subtle effect.
So this prediction of light bending wasn't entirely new with Einstein, but his theory gave a much more specific and, as it turns out, accurate number. Now, how on earth did scientists actually manage to see this bending? How did they test these predictions?
Yeah, that's the crucial part, the observation. And measurements of light deflection have actually been made across incredibly vast scales. We're talking distances from like planetary scales within the solar system, about 109 meters, all the way out to cosmological scales, maybe 121 meters or more,
Wow.
and involving objects with a huge range of masses too, from planets like Jupiter, which are a fraction of the sun's mass, up to massive galaxies and clusters of galaxies, billions or even trillions of solar masses.
That's mind-boggling. Light from basically the edge of the visible universe getting bent by some massive galaxy cluster in between us and it, like a cosmic lens.
Exactly, that's gravitational lensing. Now, closer to home, one of the most famous early attempts to confirm Einstein's prediction was during the total solar eclipse of 1919.
Ah, yes, the Eddington expedition.
That's the one. The idea was pretty clever. Photograph the stars near the sun during the eclipse when the sun's intense glare was blocked out by the moon.
Right.
Then compare their apparent positions in those photos to where they normally were in the sky when the sun wasn't nearby. They hoped to see that predicted shift, that 1.75 arc seconds caused by the sun's gravity bending the starlight.
And did they?
Well, they did see a shift, and it was much closer to Einstein's prediction than the older Newtonian one, so it was hailed as a huge triumph for general relativity. But looking back, the measurements weren't actually incredibly precise by modern standards. There were significant uncertainties.
So a groundbreaking first step, definitely, but maybe not the final word in terms of precision.
Precisely. Over the following decades, there were more refined measurements during other solar eclipses. For instance, one in 1973 gave a value for that half 1 plus gamma factor of 0.95 plus or minus 0.10.
Okay.
So consistent with GR's value of 1, but still with a fair bit of uncertainty.
Okay, getting better.
But the real leap forward in precision came with the development of radio astronomy and techniques like very long baseline interferometry or VLBI.
VLBI, how does that help?
Well, using radio waves instead of visible light has a couple of advantages. For one, you can observe sources like quasars, very distant, bright radio sources, even when they pass very close to the sun in the sky, something you can't do easily in visible light because of the glare.
Oh, okay.
And VLBI links radio telescopes spread across huge distances, sometimes continents. This network acts like one gigantic telescope, giving incredibly sharp resolution, far better than any single telescope or optical eclipse observation could achieve back then.
Ah, so by using radio waves and this VLBI technique, they could get a much clearer and more accurate picture of those tiny shifts in the positions of distant quasars as their light, or rather radio waves, passed near the sun.
Exactly. These VLBI observations, particularly from the 1990s onwards, provided incredibly strong confirmation of general relativity's prediction for light bending around the sun. For example, a 1995 measurement gave that half 1 plus gamma factor as 0.9996 plus or minus 0.0017.
Wow, that's getting really close to 1.
It is, and later analyses combining millions of VLBI observations over many years pushed that even further, getting values like 0.999992 plus or minus 0.000023. That's incredibly precise confirmation of general relativity.
That's just stunning precision. And you mentioned Jupiter earlier. Did VLBI look at Jupiter too?
Yes, getting closer to our focus today, there were indeed VLBI observations made, I think it was back in 2003, using the VLBA and the Effelsberg telescope. They specifically looked at the bending of radio waves from a distant quasar as they passed very close to Jupiter.
So even before we had these latest results from space-based telescopes we'll talk about, scientists had actually detected light bending, well, radio wave bending around Jupiter using VLBI.
Yes, that's right. That demonstrated the effect was there for Jupiter too. But missions like Hipparcos, and especially now Gaia, which operate in space and make incredibly precise measurements of the positions of stars across the entire sky, well, they've taken this whole field to another level entirely.
Okay, so let's talk about those space missions. How did this whole idea of relativistic light bending factor into, say, the Hipparcos mission back in the 90s?
Oh, it was absolutely fundamental for Hipparcos. You see, even though the most dramatic bending happens very close to a massive object like the sun, the effect, though smaller, is still measurable pretty much across the entire sky, especially when you're aiming for the kind of precision Hipparcos was designed for milli-arc-second accuracy.
Milli-arc seconds, so thousandths of an arc second.
Exactly. And to give you an idea, Even for a star observed at a 90-degree angle away from the sun, so way off to the side, the bending of its light due to the sun's gravity was still around 4 milliarc seconds.
4 milliarc seconds. That's tiny, but I guess still significant if you're measuring positions that accurately.
Absolutely, it was well above Hipparcos' measurement capabilities. So they could just ignore this subtle bending effect when they were analyzing all their data to map out star positions and motions.
So what did they do?
They had to build it in. They incorporated the predictions of light bending based on general relativity, assuming gamma equals 1, into their complex mathematical models for every single star they observed. It was part of the standard reduction process.
Okay.
But then they could do something clever. By looking at any tiny systematic differences, residuals they call them, between their actual measurements and these predictions across a whole sky, they can effectively test if Einstein's theory, specifically that gamma value, was holding up under this incredibly precise wide-angle scrutiny.
So they used the data itself to check the model they were using.
Exactly. And the analysis of these tiny differences from the Hipparcos data gave a result for that half 1 plus gamma factor of 0.9985 plus or minus 0.0015. Again, very consistent with general relativity's prediction of 1.
That's amazing. So a satellite designed primarily to precisely map the positions and motions of stars was simultaneously performing a powerful test of one of the cornerstones of modern physics.
Precisely. And while VLBI achieved even better accuracy for gamma around that time, the Hipparcos measurement was unique because it used visible light, covered the whole sky, and relied on a single instrument's calibration. It was a different kind of test.
Right, complementary approaches.
And now the same principles apply to Gaia, the successor to Hipparcos. But the stakes are even higher because Gaia's precision is aiming for micro arc seconds. That's millions of an arc second. Roughly 1,000 times better than Hipparcos in some aspects.
Micro arc seconds, that's almost unimaginably small.
It really is.
Yeah.
And this leap in accuracy meant that the mathematical models they used to analyze the Gaia data had to become incredibly sophisticated. They're dealing with such minute effects, and they have to account for a whole web of interconnected factors. Things get complicated fast.
How so?
Well, for instance, even fundamental concepts like parallax, the apparent shift in a star's position due to Earth's orbit around the sun, and proper motion, its actual movement across the sky, can no longer be treated as completely separate, independent parameters when you're working at the microarc second level. Their effects become tangled with things like light bending in very subtle ways.
It sounds like trying to measure the wobble of a hummingbird's wing from, like, across the continent. Incredible complexity.
It is a huge data analysis challenge.
Now, we've been talking about the sun and Jupiter mostly as if they're just perfect spheres of mass. But I know that's not quite right, is it? They rotate.
That's a really important point, especially when we get to Jupiter. Celestial bodies like the sun and Jupiter spin, and this rotation causes them to bulge slightly at their equators and flatten a bit at their poles. They become what we call oblate spheroids, not perfect spheres.
Like slightly squashed balls.
Exactly. And this non-perfectly spherical shape affects their gravitational pull. It's not perfectly uniform in all directions anymore.
So their gravity isn't exactly the same if you're above the pole versus near the equator.
Precisely. Scientists describe this more complex gravitational field using something called an expansion of the gravitational potential. It's a mathematical way to break down the gravity field into different components or moments.
Moments. Okay.
The first and biggest moment is the monopole moment. That's the part we consider when we treat the object as a perfect sphere, basically just its total mass. Then there's the dipole moment, which is usually 0 if the center of mass is at the center. Then comes the quadrupole moment, often labeled J2. This describes the flattening or ablateness we were talking about.
Monopole is the main mass effect. Quadrupole is the squishiness effect.
You got it. There are even higher order moments, octupole, hexadecapole, and so on, representing finer details of the shape and mass distribution. But the monopole and quadrupole are usually the most significant for effects like light bending.
Okay, so how does this more complex gravity, particularly the quadrupole part, affect the bending of light compared to just the monopole?
Right, so the monopole moment is responsible for the main bending effect we've been discussing all along. For light just grazing the sun, remember that's about 1.7 arc seconds. For Jupiter, which is much less massive but much larger, the monopole bending at its limb is smaller, around 16.27 milliarc seconds.
16 milliarc seconds for Jupiter's main effect.
Okay, but here's where it gets really interesting when you compare the sun and Jupiter regarding the quadrupole effect. The sun is rotating relatively slowly and is very dense. Its quadrupole moment only causes a tiny additional bending of light, estimated to be only about 1 microarc second, even for light grazing its edge.
1 microarc second. That's incredibly tiny, even for Gaia.
Extremely tiny. But Jupiter rotates much faster. Its day is less than 10 hours, and it's much less dense, mostly gas and liquid. This makes its ablateness, its quadrupole moment J2, relatively much larger and more significant gravitationally.
Ah, so Jupiter's squishiness is more pronounced.
Much more. And the estimated light bending caused just by Jupiter's quadrupole moment for light passing very close is around 240 microarc seconds.
Whoa, 240 microarc seconds. That's way bigger than the sun's quadrupole effect, and actually sounds like something Gaia could potentially measure.
Exactly. While the sun's shape barely tweaks the light path in a measurable way, Jupiter's squishiness has a much more noticeable impact. It's over 200 times larger than the sun's quadrupole deflection.
That's a surprisingly big difference. So the fact that Jupiter isn't a perfect sphere has a much more measurable effect on light bending than the sun's slight oblateness does.
Precisely. Now there's a slight complication. This difference in how light is bent by the monopole mass versus the quadrupole shape has a geometric similarity in terms of how the deflection changes with angle to both the overall light bending effect and the way parallax shifts a star's apparent position. They all change as the star moves relative to Jupiter.
Uh-oh. So are they all mixed up together? How can you tell them apart?
Luckily, they don't depend on the angular separation between the star and Jupiter in exactly the same way. For instance, the main light bending goes roughly as the cotangent of half the angle, while parallax goes as the sine of the angle. The quadrupole effect has its own specific angular dependence, too.
Ah, subtle differences in the geometry.
Right. These subtle differences in their mathematical form, combined with observing the star over a period as the angles change, allow scientists, in principle, to disentangle these different contributions when they analyze Gaia's incredibly precise measurements, even though the effects can be somewhat correlated in the data.
Okay, that's clever. So we've got very strong confirmation of the main light bending effect, the monocle part for both the sun and now Jupiter. But what about this more subtle effect from Jupiter's shape, the quadrupole moment? Has that actually been measured yet?
Not definitively, no. As of the analysis we're discussing, while scientists have predicted its existence and its approximate size, that 240 microarc seconds near the limb, actually isolating that specific tiny quadrupole signal from the much larger monopole effect, which is tens of milliarc seconds, has been a real challenge. It hasn't been convincingly extracted from the noise and other effects yet.
But this is where Gaia's recent observations of Jupiter really come into play, right? I seem to recall reading that one of the explicit science goals for the Gaia mission was to make these kinds of very precise tests of general relativity, including potentially measuring effects like this.
Absolutely. Even in the early planning stages for Gaia, the reports highlighted its potential to measure that key ppn parameter gamma, related to light bending, with unprecedented accuracy. Now, because of the way Gaia scans the sky, it generally avoids getting too close to the sun to protect its sensitive detectors.
Right, avoids the sun.
However, it does have opportunities to observe stars that pass very close to Jupiter in the sky. These close encounters are still tricky, mind you, mainly because Jupiter is so bright, and the scattered light from the planet can interfere with measuring the faint star nearby.
So getting really close to Jupiter is crucial for trying to detect this quadrupole effect, presumably because its influence drops off faster with distance compared to the main monopole effect. Is that right?
Exactly. The monopole deflection falls off slower with distance than the quadrupole deflection. So the closer you get, the relatively stronger the quadrupole signal becomes compared to the monopole. That's why these very close passes are so valuable.
And someone actually predicted these close passes would happen.
Yes, a study back in 2014 by Kleiner and Migyard looked ahead at Gaia's planned scanning pattern and Jupiter's path across the sky. They identified some particularly promising close encounters between background stars and Jupiter that were predicted to occur in February 2017. They found 3 stars expected to pass within about 6 times Jupiter's radius.
6 Jupiter radii? That sounds pretty close. And Gaia actually managed to observe these events.
Yes, it did. The spacecraft gathered a wealth of high-cadence observation data during a window between February 22nd and 26, 2017, covering these predicted events. The closest star observed passed just 7 arc seconds from Jupiter's limb, its visible edge. That's incredibly close.
7 arc seconds. Wow. Was the star bright enough to see easily that close to Jupiter?
This particular star was relatively faint, actually about magnitude 12.78 in Gaia's G band. But Gaia is sensitive enough, and crucially, because of its scanning motion, it observed this star multiple times as it swept past Jupiter. It got 25 individual measurements, or transits, of this star in just those few days.
That's a lot of measurements for one star zipping past Jupiter. What kind of analysis was needed to actually pull the light-bending signal out of all that data, especially with Jupiter right there?
Oh, it was a very complex and painstaking process, because they were looking for such incredibly tiny shifts in the star's apparent position. Remember, the main effect is only around 10-15 milliarcseconds, and the quadrupole is sub-milliarcsecond.
Uh,
They had to meticulously account for a whole range of very subtle instrumental and astrophysical effects.
like what?
Well, there was the scattered light from Jupiter itself, which could bias the measurement of the star's center. There's differential aberration, the slight apparent shift in the star's position due to Gaia's own velocity changing slightly across its field of view. There are tiny differences in the star's own proper motions that need to be accounted for. And even the main light-bending effect itself isn't perfectly constant across Gaia's view. They had to model that nonlinear differential light deflection, which, near Jupiter, is dominated by Jupiter's monopole.
Wow, so it was like peeling away all these layers of subtle effects, each one maybe tiny on its own, to try and isolate the gravitational signal they were really interested in.
Precisely. It required very careful modeling of Gaia's instrument and the whole astronomical situation. And the main result from this detailed analysis was a very clear, unambiguous measurement of the light bending as the star passed close to Jupiter.
And what did they find? How big was the bending?
They measured a total deflection of around 10 milliarcseconds at the point of closest approach for that star, just 7 arcseconds from the limb. Now, technically, this measured deflection is the combined bending caused by both Jupiter and the Sun, as the Sun's gravity is still acting across the whole solar system. But at such a close distance to Jupiter, the dominant contribution to the differential bending across Gaia's field of view was overwhelmingly from Jupiter's main monopole gravity. And what's really significant is that this measurement was made with a very high degree of confidence, a signal-to-noise ratio of about 50 at the closest approach.
Signal to noise of 50. That sounds like a really solid, undeniable detection.
It absolutely was a very strong confirmation. This represents the closest optical measurement ever made of light bending near Jupiter's limb. And it also had the highest signal-to-noise ratio achieved for this kind of light-bending measurement near Jupiter at any wavelength, including those earlier radio VLBI measurements.
That's fantastic. And how did it compare to the predictions?
Importantly, the results were in excellent agreement with what Einstein's general relativity predicts for the combined monopole bending from Jupiter and the Sun at that distance. There's even a compelling plot they produced, showing Gaia's measurements tracing out the predicted curve of light deflection as the star passed by Jupiter. It matches beautifully.
That's incredible visualization. So while this stunningly confirms the main light bending effect around Jupiter with unprecedented optical precision, what does it tell us about the possibility of finally measuring that even tinier effect from Jupiter's shape, its quadrupole moment? Does this get us closer?
Well, yes, these observations have really paved the way. They've definitively shown that Gaia is capable of making these incredibly precise astrometric measurements right in Jupiter's bright neighborhood, despite the challenges. That's a huge step.
Okay.
The next big challenge, then, is to try and isolate that much smaller component of the bending of the part, specifically due to Jupiter's quadrupole moment. Remember, it's predicted to be only around 100 microarcseconds or so along Gaia's scan direction, even at the closest approach. It's buried within the much larger milliarcsecond scale monopole effect.
So it's like trying to hear a tiny whisper right next to someone shouting, a very subtle signal they're trying to pick out from a much stronger one.
Exactly. It requires pushing the analysis and the understanding of Gaia's systematics even further. But the good news is that the data analyzed for this initial report only covered observations up to May 2017.
Ah, so there's more data.
Yes. There were other predicted close encounters between stars and Jupiter, similar to the ones in 2017, that occurred later, specifically in September 2018 and April 2019. Those observations should be included in future releases of Gaia's data archive, like Data Release 4 and beyond.
So more chances to look.
Exactly. These additional events, possibly with different geometries or maybe even closer passes, will provide more data points and more opportunities to try and average down the noise and potentially tease out that faint, elusive signature of Jupiter's non-spherical shape bending the light of distant stars. The hunt for the quadrupole deflection is definitely on.
This is just remarkable to think about. So take a step back. even a planet, a planet as familiar as Jupiter in our own solar system, is subtly warping the fabric of space-time around it. And it's bending the light from distant stars in a way that precisely matches a theory general relativity developed over a century ago.
It truly highlights the enduring power and incredible accuracy of Einstein's theory. And the fact that we now have instruments like Gaia capable of measuring these almost infinitesimally small effects, well, it allows us to probe the finest nuances of gravity. We can even start to seriously study the influence of a planet's physical shape on space-time itself. It's quite profound.
It really makes you think, doesn't it? I mean, if gravity can do something as seemingly strange and counterintuitive as bend light, what other unexpected ways might the fabric of space and time behave that maybe we haven't even fully discovered or understood yet?
That's the big question always.
It's amazing to realize that these incredibly precise observations, they don't just confirm our existing theories, which is amazing in itself, but they also push the boundaries and open up new possibilities for exploration, for maybe finding deviations, or for making potential breakthroughs in our fundamental understanding of the universe.
Indeed. It's a constant process, isn't it? A constant reminder that our picture of the cosmos is always evolving, always becoming clearer, thanks to ever more sophisticated tools, and frankly, just a persistent human curiosity about how everything works.
Well, thank you so much for taking this deep dive with me into the truly fascinating phenomenon of gravitational light deflection, especially around Jupiter. It's certainly given me, and hopefully you listening, a newfound appreciation for the subtle yet profound ways in which gravity shapes our universe.
My pleasure. It's a fascinating topic.
And thank you to you, our listener, for joining us on this journey of discovery today.